Hello, welcome back to the lecture series on digital electronics, which is a subject in third semester diploma ETCE. Course code is ETCE/DE/S3. I am Balusridhar, Assistant Professor, Department of Electronics and Communication Engineering, Guru Nanak Institute of Technology. Welcome back, and let's start the lectures. In the previous lecture, that is in lecture number 1, we have studied about the syllabus, and we have seen there are 7 units in the syllabus, and we have seen the objectives the students have after studying the digital electronics subjects. Next is the overview of the subject along with the introduction. In the introduction, we had studied about the digital and the analog systems, the advantages of the digital systems and the disadvantages of the digital systems, and the different aspects of the digital logic circuits, how to design the logics, how to design the circuits, the aspects of the circuit designing, and all these things. So today we are going to start the unit 1. Today we are going to start the unit 1, that is the number systems and the basic logic gates. In the number systems, we are having introduction to binary, octal, decimal, hexadecimal number systems and the conversion of the number systems. We know, or we will know, that there are 4 number systems. First one is the binary, octal, decimal and the hexadecimal number systems. After knowing each of the number system individually, that is knowing what is the base, what is the radix, which one is the positional weighted system, what is MSB, what is LSB, and what is a beat, what is a digit, all these things. After learning all of these things, we will go to the conversion of the number system, that is converting a number from binary to octal, or decimal to octal, or hexadecimal to octal. All these conversions are also very important, and please listen it carefully. That is the conversions of the number system. So we are going to start with the decimal number system. The decimal number system is the most common or the familiar number system. Now we can see the first point is the decimal number system contains 10 unique symbols. What are the symbols? First is 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. That is starting from 0 to 9. These are the unique symbols for symbolizing the digital number system. As there are 10 symbols, that's why the base or the radix is 10. Now there is no symbol for its base. That is, suppose a number is given, 21, and in the base there is nothing given. So what you will consider that the number is a decimal number system. Normally, let me show you, normally we are writing just normally we are writing, suppose we are writing 67. Okay, now the base will be like this. The base is like this. Just look here. The base is written here. That is B. Small b is written here. It is B. Small b is written here. This B is in subscript. This B will be in subscript. This B will be equal to 10 in the case of the decimal. But in the case of decimal, normally nothing is given in the case of a base. That is only 67 is written. Whenever a number will be written, just the number will be written without a base, then this number is a decimal number system. You should consider this one, that this number is a decimal number system. This is a very important thing, because this thing you will You will need it when you will be designing, or you will be doing the complex number system problems, which are very important for gate examination also. So please remember this thing, that a number without a base, that is, suppose a number is 21, and in the bracket, after the bracket subscript b, nothing is written, that is just a number is written, then the number is a decimal number. Now next point is, it is a positional weighted system. Now, what is the meaning of a positional weighted system? This has got some unique meaning. It means that the value attached to the symbol depends on its location with respect to the decimal point. That is the meaning of a positional weighted system. Now, in this system, each symbol in the number is called a digit. Now, each of these individual numbers, this suppose 2, 4, 5, all these are called a digit. Now, next point is a very important point, that is the most significant digit. What is the most significant digit? The leftmost digit in any number system which has the greatest positional weight out of all the digits present in the number is the most significant digit. Next is least significant digit. Again, this least significant digit is also very important. This least significant digit signifies the rightmost digit in any number system which has the least positional weight out of all the digits present in the number is the least significant digit. Now this, what is the short form of MSD? The short form of MSD is MSD, and the full form is most significant digit, and the short form of least significant digit is LSD, and the full form is least significant digit. Now these two things are very important because this number systems are positional weighted system, and each of this number gives us some position, that is, it should be either it is a most significant digit or it is a least significant digit. Suppose you are having a number, suppose I'm writing a number 890. Now here this one, this 8 is a MSB or MSD, and this one, this 0 is the LSD, because this one is the rightmost digit and this 8 is the leftmost digit or the leftmost digit. So this number is a decimal number, and we can know the MSD and the LSD from this number. I hope it is clear from this. Now this MSD and the LSD, this has got huge importance in all the number system. In other number system apart from the decimal number system, it is represented as MSB and LSB. Why? Because in decimal number system each of the symbol is called a digit. That's why it is most significant digit or MSD, and least significant digit or LSD. But other number systems, it is MSB and LSB, that is most significant bit and least significant bit. I hope the most significant digit and the least significant digit are clear to all of you. We're going to the next slide. Now, digits on the left side of the decimal point form the integer part of a decimal number, and the digits on the right hand side of the decimal number forms the fractional part. This is also very important. Suppose a number is given, so the left hand side will be the integer part and the right hand side will be the fractional part. Now another thing is very important, that in this system any number, either it can be integer, fraction or mixed. Mixed means it will consist of integer also, fraction also. Suppose a number is 77.7. So 77 is the integer part and 0.7 is the fractional part, and this number is a mixed number. So all of this mixed numbers, fractional, integer, all of this in of any magnitude can be represented by the use of this 10 symbols only. By using the 10 symbols, that is from 0 to 9, we will be designing the decimal number system or writing the decimal number system. Now let us see the general value of the mixed number system. Before writing this, before looking into this, let us hear something. That is, suppose the left digit to the first digit to the left of the decimal number or the point has a weight of unity or 10 to the power 0, and the second digit to the left of the decimal point has a weight of 10 to the power of 1 or 10, and the third has a weight of 100 or 10 to the power 2, and it goes on like this. So suppose this is the point, this whole one is the integer one, this whole one is the integer part, this whole part is the integer part before the point, this whole part is a, this one is the integer, and this one is a fractional part. Now from here, this point we will start counting. This one is the first digit to the right hand side, so it will be having 10 to the power of 0 power, because this is 10 to the power 0. This d1 will be having 10 to the power of, the weight will be 10 to the power of 1, and it goes on like this, and this one will be having d minus of 1, d minus of 2. Each of this denotes the digits, and this point is the point, and this denotes the integer part, and this denotes the fractional part. That is, this is the first digit to the left of the decimal point, so it has got the unit or the weight of 10 to the power of 0, and this unit, this is the second one, so it is having 10 to the power of 1. This one after the d1 here, it will be d2, so it will have weight of 10 to the power of 2. Now this one is the first digit to the right of the decimal point, so it has weight of 10 to the power of minus 1. That is, it is, that's why it is written d subscript of minus 1. That is, the weight is 10 to the power of minus 2. This is the second one, so it is 10 to the power of minus 2. It goes on like this, and this whole value is the value of any mixed decimal number. Now let us consider some number and see how it works. Let us consider one number and see how it works. Now suppose this is a number 9256.26. This one is the integer part of the point, this is point, and this one is the left hand side. So this is the integer part, and this one is the fractional part. Now how to represent this one? We can represent it like this, point. So this positional unit is, or the weight is 10 to the power of 0. So you can write, it starts from here 0, 1, 2 and 3. So you can write it like this, that is 9 into 10 to the power of 3 plus 2 into 10 to the power of 2 plus 5 into 10 to the power of 1 plus 6 into 10 to the power of 0. After this, this is the right hand position after the point. So this one will be having the weight of 10 to the power of minus 1, that is 2 will be having the weight of 10 to the power of minus 1, and 6 will be having the weight of 10 to the power of minus 2. So this is plus of 2 into 10 to the power of minus 1 plus 6 into 10 to the power of minus 2. As I have already told you, the decimal number system is a positional weighted system. So each of the position will be having some weight. And according to the point, as this is a mixed number that is consist of integer and the fractional part, the right hand side is the fractional part and the left hand side is the integer. This is the integer and this is the fractional part. So this point is here. So this one is the right hand side first point, sorry, left hand side first point. So this one is 10, the weight is 10 to the power of 0 of 6. 5, the weight is 10 to the power of 1. In the case of 2, the weight is 10 to the power of 2. In the case of 9, the weight is 10 to the power of 3. So it goes on like this. So see this one, this is like this point, and here there is a point. After this point, this is the right hand side. So it is 2 into 10 to the power of minus 1 and 6 into 10 to the power of minus 2. This one is a fractional part. I hope this is clear to all of you. Next is the binary number system. In the case of a binary weighted system, the binary number system is also a positional weighted system. The binary number system is also a positional weighted system. The binary weighted system is also a positional weighted system. The base or the radix of this number is 2. Why? Because it has got two independent symbols. The two independent symbols are 0 and 1. As previously I had already told you that digital systems deals with two numbers, that is 0 and 1. So it is a bistable devices are used. That's why it is having two voltage levels already explained, that is high and low. So 0 means low voltage and 1 means high voltage levels. As is in the case of a binary number system consists of two independent symbols such as 0 and 1. Now a binary number system is a sequence of bits, each of which is either 0 or 1. And the binary digit is also called a bit. This is a new concept, that is a binary digit is also called a bit. In the case of a decimal number system, there was a digit, but in the case of a binary number system, the binary digit is called a bit. Now each digit carries a weight based on its position relative to the binary point. The weight of each bit position is 1 power of 2 greater than the weight of the position of its immediate right. The first bit to the left of the binary point has a weight of 2 to the power 0, and that column is called the units column. The second bit to the left of the weight of 2 to the power 1, and it is the 2s column. It goes on like this. This signifies the weights. Now next important thing is MSB and the LSB. Already I have explained that MSB is most significant bit and LSB is least significant bit. So now we will see how we can differentiate between the MSB and the LSB from a number. Now suppose this is the number 000 and 1111. So we have to denote which one is the MSB and which one is the LSB. Now this is the leftmost position or the digit or the bit, that's why it is the MSB. That is the most significant bit, and this position or this one will have the highest positional weight, and this one will have the lowest positional weight. This one will have the lowest positional weight. So now suppose we want to see the weights of each of this one. So it starts from here. It is 2 to the power of 0, as it is a binary, so the base is 0. Sorry, the base is 2, so it starts from 2 to the power of 0. This one is having weight of 2 to the power of 0. This is having 2 to the power of 1. This is having 2 to the power of 2, 2 to the power of 3. Next, this 0 is having 2 to the power of 4, 2 to the power of 5, and 2 to the power of 6. So it starts from 0 to it ends at 6. Each of this is having some unique weights according to the position. As this one is the MSB, this bit is having the highest weight, that is 2 to the power of 6, and this one is having the least weight, that is 2 to the power of 0. That's why it is LSB, that is least significant bit, and this one is the MSB, that is the most significant bit. Next, if we have understood MSB and LSB, we are going to the conversions. As we have already done the binary and the decimal number systems, and we know all the things about the binary and the decimal number systems, so we are going to do one problem. What is the problem? We have to convert this number is in this binary number. Why? How can we understand that this is a binary number? Because it consists of 1 and 0s. This is the combination of 1 and 0s. Also the base is given as 2. We have to convert this number, that is 10101 base 2 to decimal. So how we should be converting it? Binary numbers can be converted to their decimal equivalents by the positional weights method. Already in this example, I have told you all the positional weights. We will be just applying this positional weights in this number. In this method, each binary digit of the number is multiplied by its positional weight and the product term is added to obtain the decimal number. Let me again tell you this. In this method, each binary digit of the number is multiplied by its positional weight and the product term is added to obtain the decimal number. Now we will be writing the positional weights here. These are the positional weights. We are writing from 2 to the power of 0, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4. And after that, we are just writing the number like this. That is 10101. So what is the weight of this 2 to the power of 0? Again, this 0 is 2 to the power of 1. This 1 is 2 to the power of 2. This 1 is 2 to the power of 3. And the positional weight of this 1 is 2 to the power of 4. So we have to just multiply the weights with the numbers, individual numbers, and do the addition. Now suppose this is 1 into 2 to the power of 4. Next is this 0 plus of 0 into 2 to the power of 3. Next this one will come. So this one is plus 1 into 2 to the power of 2. Next is again this one, this 0, 0 into 2 to the power of 1. And next is this one, 1 into 2 to the power of 0. So ultimately it will be coming, this one will be coming 16. 0 into something is 0. Again 1 into 2 to the power 2 is 4. So it is 4. Again this one is 0 into something is 0. And this one will be coming 1. As 2 to the power 0 is 1. Anything to the power of 0 is 1. So ultimately the result is 16. If you have not understood it, again let me make you understand like this. This one is having positional weight of 2 to the power of 4. So just do it like this. 1 into 2 to the power of 4. This 0 is 0 into this one, 2 to the power of 3. This one signifies again this 0. This 1. This 1 is 1 into 2 to the power of 2. This one. This is the positional weight multiplied with 1. And this 0. This 0 is 0 into 2 to the power of 1. This one signifies. And this one. Left one is this one. This one is 1 into 2 to the power of 0. So ultimately we are getting the result like this. I hope you have understood it. Hope you have understood this one. So we are going to the next slide. Next is the conversion of another number, that is the binary number to decimal conversion. Now before this number, that number did not have any fractional part. But this number, this particular number is a mixed number. This one consists of integer part and the fractional part. So how to find the decimal equivalent of this binary number? We have to see it. Now just write the positional weights. This there is a point here, so you have to write. If there is a point, you know, for the fractional the powers will be minus of something. So that is 2 to the power of minus of 1. So just write it like this. The positional weights 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4. These are the positional weights, and in the right hand side it goes on like this: 2 to the power of minus 1, 2 to the power of minus 2, 2 to the power of minus 3. So just write the number like this. Here is a point. For your clarification, let me write the point like this. The point is here. The point is here. The point is here. That's why it is 2 to the power of minus 1, 2 to the power of minus 2, 2 to the power of minus 3. Already I have told you it in the previous slides. So there will be a point here. So just what is the rules? You have to multiply the number with the positional weight and do the addition. Similarly, we have done it like this. So we have written the number like this: 11011 point. We are writing 101, 101. So just write 1 into 2 to the power of 4. 2 to the power 4 is the 2 to the power 2 to the power somethings are the positional weights. So write 1 into 2 to the power of 4 plus 1 into 2 to the power of 3 plus 0 into 2 to the power of 2 plus 1 into 2 to the power of 1 plus 1 into 2 to the power of 0 plus 1 into 2 to the power of minus 1 plus 1 into 2 to the power of minus 2 plus 1 into 2 to the power of minus 3. From here, we are getting the result as 16 plus of 8 plus of 0 plus of 2 plus of 1 plus of 0.5 plus of 0 plus of 0.125. So the result is this one, 27.625 to the base of 10. If you don't write 10, it is okay, but you can also write it. If the digit is having, or if the number is having no base, then it will be a decimal number. Already you know this point. I hope this is clear to you. Next, we will be going for the decimal to binary conversions. As we have already done the binary to decimal conversion, so we will be going to the converting the numbers to decimal to binary conversions. The decimal to binary conversions are of two types. First, what is the first method? The first method is called the sum of the weights method, and the second method is called the double method. Now let me tell you something about the sum of weights method. In this method, which is normally used only for small numbers, the values of various powers of 2 need to be remembered. For conversion of large numbers, we should have a table of powers of 2. In this method, known as the sum of weights method, the set of the binary weights values whose sum is equal to the decimal number is determined. To convert a given decimal integer number to binary, first obtain the largest decimal number, which is a power of 2 not exceeding the given decimal number, and record it. Subtract this decimal number, which is a power of 2 not exceeding this remainder, and record it. Subtract the successive reminders till you get a 0 remainder. This is a very important thing. You should be getting a 0 remainder. The sum of these powers of 2 expressed in binary is the binary equivalent of the original decimal number. In the similar manner, this sum of weights method can also be applied to convert decimal fractions to binary. To convert a decimal mixed fraction to binary, convert the integer and the fractional parts separately into binary. In general, the sum of weights method can be used to convert a decimal to number in any other base system. This is also a very important thing. We can use any of the two methods. The first method I have explained is the sum of the weights method, and the second method is called the double method. Now let me explain the second method. In this method, the decimal integer number is converted to a binary integer number by successive division by 2, and the decimal fraction is converted to binary fraction by successive multiplication by 2. This is also known as double method. In the successive division by 2 method, the given decimal integer number is successively divided by 2 till the quotient is 0. The large remainder is the MSB. That is, the last remainder will be the MSB. The remainders read from the bottom to top give the equivalent binary integer number. In the successive multiplication by 2 method, the given decimal fraction and the subsequent decimal fractions are successively multiplied by 2 till the fraction part of the product is 0, or till the desired accuracy is obtained. The first integer obtained is the MSB. Thus, the integers read from the top to the bottom give the equivalent binary fractions. To convert a mixed number to a binary, convert the integer and the fraction separately to binary and then combine them. Now what happens in the general, these methods can be used for converting a decimal number to equivalent number in any other basis by just replacing 2 by the base of that number. This is a very important thing, because as 2 is the base of a binary number, so if you replace 2 by any other basis, just in the case of octal on the hexadecimal, you can use this method. In the case of octal, the base will be 8. In the case of hexadecimal, the base will be 16. That is, any decimal number can be converted to equivalent number by any base system by the sum of the weights method or by the double method, repeatedly division by b for integers and repeated multiplication by b for fractions. Now, as we have seen the first method and the second method, that is the sum of the weight method and the double method, we are going to the numerical part, where we will be doing some sums related to the double method. So we will be solving some problems related to decimal to binary conversions. So here we have got an integer, that is 52 base 10, that is a decimal number, and we have to convert it into binary number. So we are using the second method, that is the double method, where we divide the given decimal number successively by 2 and read the remainders upward to get the equivalent binary number. So here we are doing the successive division and we are taking the remainder. Now suppose we are dividing 52 by 2. What will be the remainder? It will be 0. So we are writing the remainder here. Next is we are dividing 26 by 2. The remainder is 0. 13 by 2. If we divide 13 by 2, the remainder is 1. So we are writing 1 here. When we are dividing 6 by 2, it is 0. So the remainder, we are writing it here. When we are dividing 3 by 2, the remainder is 1. So again, the answer is 1. So when we are dividing 1 by 2, the answer is 0 and the remainder it will be 1 here. So we are taking the reminders from bottom to top. So reading the reminders from bottom to top, the result is, just look here, we are reading the reminders from bottom to top. That is, we are taking from this direction. That's why the arrow is in this, from bottom to top, that is in upwards direction. From downwards to upwards, we are taking the reminders. So the result of 52 to the base 10 is 110100. That is 110100 to the base 2. Why it is base 2? Because we have converted it into a binary number. Next is the next one is 0.75. We have to convert it into binary. Now the previous number was a integer number, but here the number is a fractional number. So the procedure is a little different. What is the procedure? Multiply the given fraction by 2, keep the integer in the product as it is, and multiply the new fraction in the product by 2. Continue this process and read the integers in the products from top to bottom. Now we are having the number is 0.75. We multiply 0.75 by 2. What is the answer? The answer is 1.50. So we will keep 1 as intact and we will multiply the new fraction. That is, what is the fraction here? 0.50. We will be multiplying 0.50 by 2. What is the answer? 1.00. Now we stop here. Why we are stopping? Because if we are multiplying 0 by 2, it will be 0. So we will not be getting any result here. So we are getting 0.11. Why? Because we are reading the integers from top to bottom. That's why the arrow is given in this direction. So it is 0.11 to the base 2. Why it is base 2? Because it is converted to a binary number. Next is convert 105.15 to the base 10 to binary. That is, we have to convert this mixed number. This is a mixed number. This contains of integer also and fraction also. So for converting this, we have to first convert 105 to integer, That is, we are first converting the integer 105. After that, we are going for 0.15 fraction. And after finding the results of 105 and the results of 0.15, we will be writing it together. So, what is the method of converting 105 integer to binary? We will be doing successive division and seeing the remainder. So, we are dividing 105 by 2. We will be getting the remainder as 1. We are dividing 52 by 2. We are getting the remainder as 0. We are dividing 26 by 2. We are getting the remainder as 0. Next is we are dividing 13 by 2. We are getting the remainder as 1. 6 by 2. The remainder is 0. 3 by 2. The remainder is 1. And 1 by 2. The remainder is 1. So, the reading of the remainder will be from bottom to top. That's why the result is 1101001. So the answer is 1101001 to the base 2. Why it is 2? Because it is a binary number. Next is the fraction 0.15. Now what we have to do? Already we know that we have to multiply the given fraction by 2 and keep the integer in the product as it is and multiply the new fraction in the product by 2. We have to continue this process and read the integers in the products from from top to bottom. So suppose we start with multiplying 0.15 by 2. The answer is 0.30. So we are taking the fractional part, that is 0.30 here. That is 0.30 into 2. Multiplying 0.30 into 2. We are getting 0.60. Again we are taking 0.60. 0.60 by 2. We are getting 1.20. 0.20 by 2. We get 0.40. Next is 0.40 by 2. It is 0.80. Next is 0.80 multiply by 2. It is 1.60. Now we stop it here. Why? Because this 0.60 is again occurring here. If we multiply 0.60 by 2, this results will be coming. This results will be coming. That is from, again it will be repeated. That's why we stop it here and we are taking the integers from from top to bottom. That is 0.15 to the base 10 is equal to 0.001001 to the base 2. That is 0.01001 to the base 2. So the final result of the mixed number, that is 105.15 to the base 10 is 1101001.001001 to the base 2, where the base 2 is given because it is a binary number conversion. The number is a binary number. It is the conversion of decimal number to a binary number. So in this lecture we have seen how we are converting the decimal to binary numbers, and in the next lectures we will be studying some things about the octal number system. So I'm thankful to all of you for listening. Thank you.